Hello everyone, we are going to do the Unit 4 exam review in this video. So this is for the momentum exam, and let's just go ahead and get started, shall we? I'm a little too close. There we go. All right, so this exam we have, let's see, how many questions do we have? We have to get through 12 questions, and then we have one QQT FRQ, which is the shortest FRQ. So total 20 points. Let's start working our way through the multiple choice questions. So 1, a spaceship of mass 3m is in deep space, far from any objects, traveling with a speed of 3v to the left. As shown in the top figure, the spaceship separates into two pieces, mass 2m and m. The piece of mass 2m moves to the left with 4v. What does the piece of mass 1m move to the left with the speed? Why does the piece of mass m move to the left with a speed of v? So let's run this through the conservation momentum, because it seems like this question is just going to ask us if momentum is conserved or not. So initially, we have a momentum of 3v times 3m, which is 9mv. Afterwards, with these speeds and these masses, we have a momentum of 4v times 2m plus m times v from the other smaller piece. So that's 8mv plus mv, which is 9mv. So initial momentum equals final momentum, which means momentum is conserved here. So momentum being conserved means there's no external forces on the system, which means there's no external force, so momentum must remain constant. No external forces does not mean kinetic energy needs to remain constant. It just means momentum needs to remain constant. A force probe is used to push a box, so we have a force probe pushing a box, and it looks like we have a graph of the force exerted versus the time of the box. During which time interval does the box experience the greatest change in momentum? Change in momentum is impulse, and impulse is equal to force times time. So force times time, we are given a graph of force versus time, so we're looking for the area under the curve. Which section has the largest area under the curve? That's this 4 to 6 section, which is C. When we have to multiply the two axes, that's when we look for area under the curve. When we have to divide y by x, that's when we're looking for slope. So we're looking for area under a curve here. A cart carrying sand has a hole in the bottom that allows the sand to spill out. Cart, it's moving at a speed of 1.5 meters per second, and it's spilling some sand as it moves. After a short time, the cart still has a speed of 1.5 meters per second, but 0.2 kilograms of sand has fallen out. What is the magnitude of the change in momentum? So we lost momentum here. We're going the same speed before and after, but now we have that much less mass. So our change in momentum is just going to be that mass times the speed. So 0.02 times 0.02 times 1.5, 1.5, which is 0.03 newtons times seconds, which is a valid unit for momentum. Momentum, just mass times velocity. We're just looking for the change in mass times velocity, which is we lost that much mass, which means we lost that much momentum. In a controlled experiment, when engineers test a firecracker, the firecracker has a mass of m, is placed onto a horizontal surface. When the firecracker is lit, it explodes and breaks into two pieces. In the first trial, one piece has a mass of m over 2, moves to the left with a speed with VL. The other piece moves to the right with the speed of VR. In the second trial, an identical firecracker, and one piece has a mass of 3 over 4 to the left, with a speed of VL, what will the speed of the other piece in their second trial? I think this is the one that got skipped last year, and this does look like a complicated one. So we have a firecracker, and it's just kind of sitting there. It's in a controlled experiment, and then it's gonna explode, and then it's gonna explode into two pieces. One's gonna move to the left, one's gonna move to the right. Momentum is gonna be conserved here, so this is just gonna be conservation momentum. I don't think we even need to analyze this first trial. We have everything we need in the second trial. So if the speed, so the momentum to the left, the initial momentum, let's just start there. The initial momentum is 0. It does not equal 0. Initial momentum equals 0, which means the final momentum also has to add up to be 0. So the momentum this way, let's call that momentum to the left, has to equal the momentum to the right. The momentum to the left, mass times velocity, its mass is 3m/4, and its velocity is VL. The momentum to the right, its mass, if this one's mass is 3/4m, then this one's mass is going to be 1/4m, or just m/4, and it's moving with a velocity to the right. We just have to solve for the, we're solving for, what are we solving for? We're solving for VR. Are we? Well, what will the speed of the other piece be in the second trial? So I think this question, I think I messed up this question because we're solving for VR, but these should all be in terms of VL. Okay, but anyway, let's solve for VR. Let's multiply both sides, but m's can cancel out. And if we multiply both sides by 4, 4's also cancel out, and we get 3VL equals VR. So in other words, the speed to the right is going to be 3 times the speed to the left, which is this one. Yeah, I think I messed up this. I think these are all supposed to be VLs. But if 3/4 of the mass move to the left, that means the left is going to be moving slower to the right than the right. A cart carrying a block moves to the right with a constant speed. The block does not slip on the cart. Consider the two systems. System 1 consists of only the block. System 2 consists of the block and the cart. Which of the following correctly compares the speed of system 1 and 2 and the magnitude of momentum in system 1 and 2 respectively? All right, we have this system, I guess these two systems, moving to the right with a constant speed. Their speeds are going to be equivalent. So it's not A and not B. They're both moving together. The block is not slipping, so they're both moving with a constant speed. Comparing the momentum, momentum is mass times velocity. The system 1 consists of only the block. System 2 consists of everything. So system 2 is going to have more mass, which means it's going to have a greater momentum. So P1 is going to be less than P2, which is C. All right, we had a graph represents the force exerted by a barrier on a ball as the ball collides and bounces off the wall of the barrier. The initial and final velocities of the ball have the same magnitude v, but opposite directions. Which of the following graphs could represent the force exerted on the ball if the initial and final speeds of the ball were 2v, but the contact time remained the same? Okay, so a little hard to picture what's happening here. We have just a ball colliding with something, and it comes back the other way with the speed of v. In the second scenario, we have a ball colliding with something, and it comes back with a speed of 2v. We are told that the collision times for both of these are the same. So T1 has to equal T2. So first off, these two graphs, B and D, are out because B and D, they both have a collision time of 6, whereas this one has a collision time of 2. And we're told that the collision times are equal. Okay, if the second scenario has double the speed of the first scenario, if we know that change in momentum is force times time, time is not changing, which means that force needs to be greater. Something needs to make that ball move faster. It's not the collision time, so therefore it's the collision force. And A is the one that has the greater force to change that ball's speed to make it go faster compared with this one, the first graph. A block of mass m slides along a frictionless surface with kinetic energy k. It collides with a block of mass 3m initially at rest. Let's just draw this out. The two blocks stick together. So block m is moving this way with a kinetic energy of k. So let's say that's moving just with v naught. The two blocks stick together. So after the collision, we have a system that looks like this. That's going to be moving this way with the speed of v final. That is 4m. What is the ratio of kinetic energies? So, all right, we got a little bit of work to do in this problem. So first thing we're going to do is we need to find what this v final is compared to this v initial. And to do that, we're going to use the conservation momentum. Momentum initially equals momentum final. Then we are going to compare, we're going to make a ratio of kinetic energy initial to kinetic energy final once we find out how the velocity is compared from the momentum equation. So we have a little bit of math ahead of us. Let's start with conservation momentum. Initially, this block is not moving. It has a speed of 0, so the initial momentum is just m of e naught. The final momentum, they're now together. We have a mass of 4m, v final. M's can cancel out. So v final equals v naught over 4. So the speed of the system went down by a factor of 4. Now let's looking at the total kinetic energy of the two systems. Initially, once again, this one is not going to have kinetic energy since it's not moving. So the kinetic energy of the first section is just 1/2 m v naught squared. The kinetic energy of the second system is 1/2. We now have a mass of 4m because we have all of this, and we have a speed of v naught over 4 squared. So let's simplify this. So 1/2 4m, and then we have v naught squared over 16. And then simplifying all of these, we have, when I do 4 divided by 16, that gets just, we get 1 over 4. So that's equal to 1/4 times 1/2 mv naught squared. And 1/2 mv naught squared is k naught. So that means k final equals 1/4 k initial. So the kinetic energy went down by a factor of 4. So it's going to be this one, the one that's a 1/4 ratio, and the initial kinetic energy was greater than the final kinetic energy. A ball of mass 0.5 kilogram rolls across a level surface with a momentum of 0.25 newtons times seconds directed to the right, as shown. Which of the following correctly indicates the magnitude and direction of the velocity of the ball? This one seems really easy. Okay, it's got a momentum of 0.25 and a mass of 0.5. Momentum is just mass times velocity. Okay, so 0.25 equals 0.5 times velocity. Point 0.25 divided by 0.5. Velocity is just 0.5. And then it's moving to the right, so the velocity is going to be to the right. Meters to second to the right. Velocity and momentum should always be pointed in the same direction because it's the velocity vector that's making momentum a vector as well. So they're always going to be oriented the same way. Mass is not a vector, so it's just the direction of the momentum equals the direction of the velocity. I don't know why I have a lot of doubts with this one, but like it seems a little bit too simple. All right, yeah, we're good. 9, the figure shows the speed of two identical carts immediately before the collision. After they collide, the left cart has a speed of v. So we have before collision, after collision, the left cart has a speed of v. The right cart has a speed of, we don't know. So let's find out the speed of the right cart using the conservation of momentum. So initial momentum is, we're going to call both of these have a mass of m since they're identical. So we got m times 2v plus mv. That equals final momentum. We have mv plus, and then just looking at this without even doing the rest of the math, I know that this has to have a speed of 2v in order for them to be the same. So really they just swapped velocities here. But this speed needs to be 2v in order for momentum before and after to be the same. So really, I mean, nothing much is changing here, which is true of the statements about the kinetic energy of the two-cart system to be true. None of the kinetic energy, it looks like this is perfectly elastic. None of the kinetic energy is lost. We have the same amount of mass and the exact same amount of velocity. It's just we're swapping the cart's velocities, but the total kinetic energy is the same. Two lumps of clay with mass m and 2m are traveling in the opposite directions with speed of 3v. As shown above, the lumps of clay collide and stick together. What is the speed of the combined lump of clay after the collision? Stop me if you heard this one before. We're going to use conservation of momentum. The initial momentum of the system, so we have two things moving. They're in opposite directions, so be careful. One of these is going to be negative. Let's make this one the negative. Let's say the positive direction is to the right. So the initial momentum is m times 3v minus 2m times 3v. That minus makes this one a negative. The final momentum, they're going to stick together, so the total mass is now going to be 3m, and we're solving for the final velocity. So 3mv minus 6mv is negative 3mv, and that equals 3mv final. Divide both sides by 3m. Everything cancels, and we get v final is equal to negative v. So what that means, it's going to be moving with the speed of v in this direction, which is b. All right, one more multiple choice. In the classroom at time t equals 0, a sphere is thrown upward at a 45-degree angle to the horizontal. At time t1, while the sphere is still rising, it bounces off a ceiling elastically with no friction. Which of the following pairs of graphs could represent the sphere's horizontal velocity and vertical velocity as a function of time? Okay, so we're throwing a ball up. So this is the ceiling. We're throwing a ball up at 45 degrees. And it's gonna collide within the ceiling perfectly elastically. And we have to pick which of these graphs is going to show us what's going to happen. So you kind of have to notice what a perfectly elastic collision looks like. If we were throwing this ball along a horizontal wall, a perfectly elastic collision would mean the ball just bounces right back with the same velocity, but in opposite directions. With this ceiling problem, something similar is going to happen, but it's not going to bounce back this way. What's going to happen, its vertical velocity is going to change, but its horizontal velocity is going to stay the same. So it's going to bounce like this. And it's going to come back this way with that same angle, but now it's going to be moving downward with that same velocity, that same speed. So the horizontal velocity, this component of the velocity, is not actually changing. What is changing is the vertical velocity. The vertical velocity went from this to this. So horizontal is not going to change. So it's not C and D. Vertical is going to change. And it looks like it's going to be going from up to down. It's going to be B. We're going to have this moment where we see a sharp, sudden change in velocity as it bounces. The reason these are not straight is because gravity is still a factor here. So gravity is still slowing these balls down ever so slightly and speeding it up when it's after the collision. So, but we should see this sudden change in velocity due to the bouncing of the ball. Last question, a spring-loaded launcher cart is initially at rest on a horizontal surface as shown. When the launching mechanism is released, a marble leaves the launcher with a speed of v1 and the cart moves in the opposite direction with a speed of v2. Friction forces are negligible. Is the momentum of the launcher marble system before the launch equal to the momentum immediately after the launch? Why or why not? The answer is yes, it is. It is. There is no outside force. Everything is frictionless. Friction forces are negligible, which means there's going to be no outside force on the system, which means momentum is conserved. When in doubt, momentum is conserved. Like 99% of problems, 99% of collisions that you're going to deal with, momentum is conserved. The only time there's not a momentum conserved is when there's an impulse, and usually it's pretty explicit when there's an impulse, when there's an outside force causing an impulse. So it's not no, it's yes. And yes, because there is no external force, which is A. All right, moving on to the FRQ. All right, we have these two blocks. We have block 1 sliding to the left. We have block 2 at rest. The blocks will stick together after the collision and friction is negligible. If block 2 is much less massive than block 1, estimate the approximate speed of the two-block system after the collision in terms of V0. Justify your estimate using qualitative reasoning beyond referencing equations. So what this means, if M2 is way less than M1, this picture is not doing this justice. What this means is like we have a situation that looks like this. We have M1, and it's moving with the speed of V, and then we have M2 down here. M2, so tiny. When this collision happens, it's going to look like that. If M2 is much less massive than M1, then what that means is that the initial velocity is just really going to equal the final velocity. This is like your situation where you're flying a windshield. You know, you're in your car, you hit a fly going down the highway. That fly is not impacting the momentum of your car because your car is so much more massive than the fly. If M2 is way less big than M1, then the initial speed is just going to equal the final speed. Now, in actuality, maybe it slows down a very, 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 very little much, but that's negligible. So that's what we're going to say. We're going to say V initial equals V final. I'll leave my picture there because, you know, I think that's a good thing for a grader to see so you kind of understand what's happening. If V initial equals V final, when M1 is way, way bigger than M2, then the momentum M2 or I'll say when the impulse M2 causes on M1 is negligible. Starting with the conservation of momentum, derive the equation for the speed of the two-block system V final after the collision of M1, M2, and V0. Begin your derivation by writing fundamental physics principle or an equation from the reference book. So now, how these FRQs work, first you're going to qualitatively look at the situation. Now we're going to quantitatively look at the situation. That's why it's called quantitative translation. First, we're basing the system. We're gonna picture what this system is doing, just using our physics knowledge based on vibes, and just think, okay, what's actually going to happen? Thinking through the situation. Next, we're going to mathematically calculate that and see if those two things match. And that's what the final answer is going to ask. It's going to ask, does our qualitative understanding match with what our quantitative understanding was? So we're going to use conservation of momentum here. Initial momentum equals final momentum. That's the equation we're going to start with. So the initial momentum, initially we have m1 moving with the speed of v naught. So initial momentum is going to be m1 v naught. Final momentum is going to be these two blocks sticking together, which is m1 plus m2 v final. And we're going to solve for v final. So v final equals m1 v naught over m1 plus m2. Sometimes these are hard derivations. Sometimes these are easy derivations. I would say this one was a pretty easy derivation. But that's our final answer. We solved for v final, and we solved it in terms of m1, m2, and v naught. If block 2 is much less massive than block 1, does the equation derived in part B agree with your qualitative reasoning from part A? I would say it does. Yes, it does. If M2 is much less massive than M1, then what we can say just say that M1 plus 2 is just M1. Okay, sometimes it's hard to think in variables. Put numbers to these. If M1 is way more massive than M2, let's say M1 is 100,000 kilograms, and M2, this little guy, is 0.1 kilogram. Then M1 plus M2 would be 100,000.1 kilograms. That is a negligible difference than just the mass of M1 by itself. So if M1 is greater than M2, then really this bottom portion, then what we can say is that V final is equal to M1 V initial over what really just amounts to M1. The more big M1 is to M2, the more our equation is going to realistically look like this. And then M1 over M1 is really just this, where you get V final is equal to V initial. So just putting that in words, if M2 is less than M1, then M1 plus M2 equals 0. The denominator of the equation will simplify to M1, and the equation further to V final equal V initial. All right, that does it for this exam. Just final thoughts on this FRQ. Really just have a good understanding of what collisions look like. You guys have seen collisions. You guys know collisions. I don't have to explain to you what a collision looks like, hopefully. You have prior knowledge in that. Just make sure you're really with momentum, making sure that things make sense. That's a really big thing with momentum. We kind of know what's going to happen when two things collide. Like, for example, going back to, I want to say this one right here. If we have, let's clear this. If we have these two objects running to each other, they're moving the same speed, they're going to stick to each other, and one has a mass of m, the other has a mass of 2m, we know that realistically what's going to happen is these two objects are going to move this way. This one is going to overpower this one, and they're going to move with a speed to the left. Also, that speed is not going to be as big as it was before, because a lot of that speed is going to be lost in the collision as their masses go up. Just based off of those, we could already kind of eliminate 0 and 3v. If this was not asking about speed and it was asking about velocity, and like maybe 2 of the 8 questions had the wrong sign for velocity, and we can just get our answer based off of vibes and not having to do any math at all. So really just use your noggin when it comes to these collision questions, and ask yourself, does this make sense before and after the collision? All right, that's it for this one. Good luck on your studies. Good luck on your tests, everyone. And I'll see you back in class. Let me know if you have any questions.